Welcome back to HackCode. In this video, we're going to tackle an essential problem for code interviews, House Java 2 from LeetCode. This problem is great for learning dynamic programming with circular errors. It's an important concept that builds up on House Java 1 problem. So if you haven't already watched it, check out the video about House Java 1 for a solid foundation. The link is in the description and also you can find that in the I button on the screen. So we'll explore 4 approaches: recursion, dynamic programming, top-down, bottom-up, and a space-optimized version. Let's break down the problem step by step and understand how the solutions work. So sit back, relax, and let's dive in. So firstly, let's look at the problem statement. You are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. All houses at this place are arranged in circle. That means that the first house is the neighbor of the last house. Meanwhile, adjacent houses have the security system connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. So given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. So you got the scenario, right? So if you have already seen that house number one, you have got the complete context. But let me just explain you. So here we have circular houses, but in house number one we have a plain straight houses. Okay, it was a line-wise houses, but here it's circular houses. So here the last house becomes the neighbor of the first house. So here we have an array 1 2 3 1. Then 1 and 1 are neighbors here. Okay, so right, the security systems between the two houses are connected. So if you rob these two houses, then a call will be going to police. So we should not alert the police, but still we should be able to rob and get the maximum amount. Okay, so that's the idea here. Let me just explain you with the examples. So firstly, we have nums is 232. In this we have only three houses. So here you can rob only one of this. Basically, these three are connected, right? So 2 is neighbor of 2 and 2 is neighbor of 3 and 3 is neighbor of 2. So in this case, you can only rob the max out of these three houses. So maximum is 3. So that's why we output 3, because that is a maximum amount you can rob without alerting the police. Okay. So an example 2, we have 1 2 3 1. So here in 1 2 3 1, what is the maximum you can make without alerting the police? So that is 1 and 3. Okay. So if you make 1 and 3, the police won't be connected because this is not adjacent. It can be opposite or somewhere, but it is not adjacent. That's what the idea. So there won't be any alert going to police and we can rob it here. Okay. So 1 3 is our choice and we'll get 4 money. Okay. So here the same explanation is given. So rob house 1, which is money 1, and then rob house 3, which is money 3. Then the total amount you can rob is 1 plus, which is 4. And our example 3 says 1 2 3. So here is the same scenario as the first example, right? So if only 3 houses, we can rob maximum out of these 3 houses because these 3 are connected adjacently. So forget this case, like if you have only 3 houses, like they are connected like this. So in this case, we have this 2 connected and we have these 2 connected. So you can rob only one of this. So for that case, you have to pick the maximum of these 3, which is 3 here. Okay. So let's look into constants here. So num's length is an inclusion range of 1 to 100. That means that in the best case, we have nums given as length 1 only, and the worst case, it goes up to 100. So let's consider n is equals to 100. In that case, we can perform till n power 4 operations because we know that we can perform 10 power 8 operations per second. So till n power 4 complexity, the solution is accepted. Okay, so we can propose a solution whose complexity is less than or equal to n power 4. So till that range, it is acceptable for this. Okay. So keep this in mind, only 10 power 8 operations are possible per second. So based on that, we have to form our solution. Okay. If n is equals to 100, we can go till 10 power 4. So if they give n is some 10 power 4, then we can go only till n square, that is 10 power 8, right? So based on the constraints only, we have to form the solution. Okay. Next constraint is nums of I is the inclusion range of 0 to 1000. So basically the money within the houses or the element in the array is in the inclusion range of 0 to 1000. Okay. That's what the constraints we have. So this is the boilerplate code given, wherein we have a method rob which takes the nums, which is a list of integer, and returns the integer. This integer is what the maximum amount of money you can rob without alerting the police. Okay, let's look into the approaches. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. Now let's look into a brute force approach with recursion. So basically here, the problem statement asks us to not to rob from adjacent houses. So here, if you take a linear array case, these two become adjacent. But if you take a circular array case, the ending and the starting becomes adjacent, right? So basically 1 2 3 1, here 1 and 1 becomes adjacent. So what if we convert this into a linear case? So we can rob from 1 to 3 and 2, 3, 1 and compare the maximum we can get out of these two. Then it would be similar to house number 1. So basically here we're splitting the problem into two. Okay, first is we're robbing from 1 to 3 and next we're robbing from 2, 3, 1. So after robbing these two, we compare the maximum out of these two possibilities. Because even if we take the circular case, here we can't rob from these two, right? So either we rob this one or this one. So we're just considering the two cases. We pick from 1 to 3 and then 2, 3, 1. Okay, we have to exclude one of this. Okay, so that's what we're doing here. That's how we're converting our circular array problem to the linear array problem. Okay, so let's look at the intuition. So this approach explores all possible combination by recursively choosing to rob or skip each house. Since each house is arranged in circle, we can solve it by considering two cases as we just discussed. So rob houses from index 0 to n minus 2. So this is robbing from 1 to 3. And next rob houses from index 1 to n minus 1. This is robbing from 2, 3, 1. So basically we are skipping one index each time. Okay. So we can use recursion to calculate the maximum profit for each range. Okay. So let's look at the algorithm. So define a helper function to calculate the maximum profit for robbing with the given range. So if start greater than n, return 0. So why start greater than n? So here we have the indexes defined, right? That is start index and end index. So if start index greater than end index, that it means that we explore all houses and we don't need to explore further, and we won't get any value out of it. So that's why we return 0. Okay. So next step, calculate the profit by robbing the current house or skipping it. So basically, we can either rob the current house or skip it. We can make this decision based on the profit we're getting. Okay. So return the maximum profit between robbing or skipping the current house. So you know, right, basically we have two choices for each house. We can rob or skip. So we have to return the maximum out of these two, robbing or skipping. Okay, so if you rob the current house, you can't rob the next house. So if you skip this current house, you can rob the next house. But based on what we make decision, it's based on the profit we get, right? So that's what these steps are about. Let's look into the code, which should give you more idea. Okay, so here we define a helper function which takes the start and end. So both are integers. These are the indexes we have. Firstly, we rob from 0 to n minus 2 index. And next is from 1 to n minus 1. So here n is what? Length of the array. Okay. So first is the base case. If start greater than n, return 0. So here this means that all valid indexes are exhausted. That means we already explored all the houses we have. So that's why we don't have anything to rob and we return 0. Okay. So without this base case, this recursion would keep on happening and it would give us recursion depth exceeded error. And next step, we calculate the profit by robbing the current house. So basically we pick the value of the current house by collecting nums of start, and then we call this function recursively. We pass start plus 2 and end. So basically here start is what the index we pick, right? So we pass start plus 2 to say that we don't drop the next one, but we can drop the next but one. That means that if we consider start is here, we'll pass plus 2, which is third one. Okay. So that's how we're skipping this house and then we're robbing this house. So you got the idea, right? So that's what we have the value for rob current. Okay. And then next is skip current. So if we skip current, we can rob the next house. That's why we're passing start plus 1 and end. So here we are not considering the nums of start. That means that current value is not considered. So it is not robbed. Okay. So in step 4, what we do, we return the maximum profit between robbing or skipping. So that is max of rob current and skip current. Okay. This is the helper function we have. Okay. So before invoking the helper function, we have the edge case to handle, right? That is nums is of length 1. So when nums is of length 1, we don't need to consider any calculations, right? We can directly return nums of 0. That is the only house we have and it's the only choice we have, right? And it's the only thing we can rob. That's why we return nums of 0. Okay. In step 4, we calculate the max profit by considering two cases. So what is two cases here? This 0 to n minus 2 and 1 to n minus 1. So we pass the start and end indexes accordingly. So here we passing what? Helper of 0 and length of nums minus 2. This is the case of 0 to n minus 2 and this is the case of 1 to n minus 1. And then we're picking the max out of these two possibilities. Okay. So that's it, guys. It's a basic thing. We just need to convert the circular array problem into the linear array problem. Okay. Which is then like just like a house robber one only. So what are complexities here? The time complexity is O of 2 power n because each house generates 2 recursive calls. So for each house we have the two choices to make, right? So if we take a particular house, either we can rob it or skip it. Okay, so how many such houses we have? Houses. So each house generates two possibilities. So we have to multiply 2 till what? N times. That means 2 power n, guys. So next is space complexity. This is O of n due to recursion stack depth. Okay, so recursion stack depth would be of what? Length of the array. So that's why it's O of n. So I got the code ready here. Let me try running this. So this accepts solution for the 3 cases. Let me try summing this. So guys, we see the time limit is exceeded. This is because we have exponential time complexity and this won't be scaled for the larger arrays. So only 53 out of 75 test cases are correct. That means that our logic is correct, but just that the solution is not optimized. So let's explore how do we optimize this, okay? So let's look at the recursion stack. So firstly, let's consider nums as 2, 7, 9, 3, 1. So here we would be having two cases, right? So first we consider 0th house to second last house, and next first house to last house. Okay. So this would call two recursive calls. So first is helper 03 and next is helper 1, 4. So for this, if we consider this particular house, then we have to call for plus 2. So that's why we do call helper of 2, 3. So here we passing start plus 2 and end is same. Okay, and next if we skip this house, we can pass plus 1 because we can rob next house and the end is same here. So similarly for this case as well, if we rob this particular house, we pass plus 2 and the end is same, and if we skip this particular house, we can pass plus 1 and the end is same. So, and we have the further recursive calls based on the same logic. Okay. So let's take the closure loop. So here if you observe, we have the redundant calculations. So this helper of 2, 3 is called again and again. So this is called once here and this is called another time here. And helper of 4, 3, this is also called twice. And helper of 3, 4, this is also called twice. Helper of 4, 4, this is also called twice. Okay, so basically we are generating the same recursive calls but in another subproblem. Okay, what if we compute this subproblem and use this result again? So that way we don't need to compute this again and it would save the computation time. Okay, that's how we can optimize this. So you're getting right what I'm talking about. It's dynamic programming, guys. So this is a case where we compute the subproblems once and we store the results, and next time we don't compute the subproblems again. Rather, we use the stored result. Okay, so let's look into this optimized approach, which is the dynamic programming based top-down dynamic programming approach. Okay, this is a memoization approach. So basically, in this approach, we use memoization to store the results of subproblems. We still consider two cases for robbing, that is in the ranges of 0 to n minus 2 and 1 to n minus 1. But we avoid redundant calculation by storing the intermediate results in the memory dictionary. Okay, so let's look at the algorithm. Firstly, we define a helper function with the memory dictionary to store results. So basically, here additional step is we declare a dictionary here. That is for storing the results we compute for subproblems. Okay. And next is this is the same step we had. If star greater than n, return 0. This is a base case, same as previous approach. So use memoized results if available. Otherwise, calculate the max profit. Okay. So as we discussed, we compute only if it is not computed before. So firstly, we check in the cache or memo. So if it is not available in memo, then we compute it and store this in memo and then we return it. Okay. So step 4 is same, return the max profit for both cases. So basically we have some minor code changes. Okay. So later part of the video, I'll show you only with one line of the code change, how can we convert this recursion into the memoized approach. Okay. So for now, let's look into this approach with the hash map. Okay. So basically here we are using the hash map for storing the results. Okay. So here if you compare the previous approach, what I'll change, this helper function takes another parameter. This is memo, which is of dictionary type. Okay, so this dictionary is actually acting as a hash map here, which is storing our results. Okay, so here this is all same. Okay, so if start greater than n, we return 0. This is same, and then this is the additional step we have. Okay, if start in memo, then we return memo of start. So basically here we storing the result in memo. So why using key as start? Basically the start is something that is different, right? So this end is always processed same as what we get. So only start changes. That's why we use start as a key here. Okay. So keep in mind, we use key as a unique elements. Here we don't require an end. Okay. So this end is always same for everything. So only thing which is varies is start, right? So even if you consider the recursion stack here, this end is always processed same. So only the start varying. So helper of 2, 3 is computed twice. But if you use key as 2, then it would be sufficient, right? That's why we're using key as start only. So step 3 remains same. This is for rob current and skip current. So after this we have step 4. This is the variation here. So there we are returning results. But here before returning we storing the result in memo of start. After that we return the result from memo of start. Okay. So this is the difference here. Basically after computing the result we storing it and then we returning from the memo we have. Okay. So that's the only difference. Rest all remains same here in this function. So here also we handle the edge case which is same. And next here as we add a new parameter to the helper function, we just pass the empty dictionary here. Okay. So that's the difference, guys. So basically we have minor code changes and it would become a memoized version. Okay. So what are complexities here? The time complexity is O of n, as each subproblem is solved only once. So here we have n houses and for each house we are computing only once. So that's why it's O of n. This is for the memoization cache and the recursion stack. So here there is recursion also happening and we storing the results in our memoization cache as well. So this memoization cache would grow till what? Till the length of the given array, which is n, and this recursion stack also would be of the length n. That's why it's O of 2n actually, but 2 is the ignorable constant, so it is O of n. Okay. So guys, as I told you before, I'll show you how to convert this recursion method to the memoized approach only with just one line change. So let me just add a at of cache here and let me submit this. So this accepts solution and beats 17% of users. So basically here, this at of cache annotation is acting as our dictionary or the hash map here. So basically this stores the result for the subproblem. So if we pass the same parameters to the helper function again, that would be fetched from the cache instead of computing it. So once we compute it, it will be stored in the cache. So that's what this annotation is helping us, and this method is converted into the memoization approach. So this is active solution. Now let's look into the actual memoization approach we discussed. So I got the code ready for the memoization version. So let me try running this. So here we're using the hash map, okay? So this is active solution for the 3 test cases. Let me try submitting this. So this is active solution and beats 100% of users. Cool, right? So let's look into bottom-up dynamic programming approach. This is basically a tabulation approach. So here the difference is we would be using iteration in place of recursion, the array in place of the hash map or dictionary. So this array would store the results of the subproblems. Okay. Firstly, let's consider the given example 1, 2, 3, 1. So here also we would be using this 2 array split. So basically it is 1, 2, 3, and next is what 2, 3, 1. So as we discussed, we would be having the array, right? So here we would be forming the DP array of same length. So let me just create a DP array. So here I'm representing this in table format 0, 1, 2, and this is the index we have, and this is the value for that particular index. So firstly, we would be initializing all to 0. So this is the installation of the array, and then we fill this. So basically, how do we fill DP of 0? So DP of 0 is what? The maximum amount of money that can be dropped till first house. That is what? Nums of 0. It's only 1. And then DP of 1. So for DP of 1, how can we decide the max amount? So basically here we have two choices. Either we drop this house or we have the previous house. So in that case, we can store what? Max of 1, 2. So basically this is the maximum amount we can drop until this point, right? So that's why it is max of 1, 2, which is 2 here. So let me just update 2 here. So next is DP of 2. So what is the maximum value we can drop till DP of 2? It is just the consideration of dropping this house. If we drop this house, we can add previous house. That is 1 plus 3. So if we skip this house, then we just have 2 in place because we don't drop this house and the value is same as previous. So here we have 2 possibilities. So what are the 2 possibilities? It's just like a max of current element value, which is 3 plus previous to previous. That is what? 1. And the possibility is what? Skipping this. So then we get the TP of 1 only, right? So basically if we don't drop this, we just get the TP of 1. Okay, so that is max of 4, 2, which is 4. So here till 2 we have 4. So what does this DP of 2 represent here? So DP of 2 represents the maximum amount of money we can drop till what? First 3 houses. So here we have only 3 houses. So till that point, if we have to return the max amount, we just need to return what? DP of -1, which is 4. Okay. And next, let's look into this case. So similarly, let me just create a DP table for this, DP and value. So we have indices and this value 0. So DP of 0 is what? Directly it is 2. And next is DP of 1, which is max of first 2, which is 3. And next is DP of 2 here. So here also what we have for DP2. So we can consider the case of skipping this or robbing this. If we skip this, that would be the value we have for DP of 1. So it is max of DP of 1. And if we rob this, what the value we have? It is 1 plus. And then DP of 0. DP of 0 is what? 2. Okay. So this is max of DP of 1 is what? It is 3. And then 1 plus 0, 1 plus 2, which is 3. It is 3. Okay. So here DP of 2 is what? 3. So if we drop 2, 3, 1, we get the maximum value as 3. Okay. So out of these two possibilities, what is the maximum? It is 4, right? So that's why we return 4. Okay. It's the same intuition, but just that we use iteration and tabulation. Okay. So let's look into the algorithm. Step 1, create a dynamic programming array to store the maximum amount of money that can be robbed up to each house. In step 2, insert the first house with its value and the second house with the maximum of first 2 houses. This is what we just did, right? So in step 3, iterate through each house starting from the third one. Calculate the max profit at each step by considering whether to rob the current house or not. Okay. So this is the formula we had, right? So basically here the formula is what? Max of DP of I minus 1 and nums of I plus DP of I minus 2. So this is the formula. Okay. So this is just like considering if you have to rob this house or not. Okay. Step 4, return the maximum amount from the last house. Okay, so basically here this DP of -1 stored the maximum amount we can draw till that many houses, right? That's why we return the last element. Okay, so now let's look into the code. So firstly, we are handling the edge cases, guys. So this edge cases means that we don't even need to form the DP array. So if you have a nums of length 0, then we don't have any houses. We just return 0. So this won't happen, but just the case I added. So I told this won't happen because we have nums is length 1 always. That's why we don't have this case, but I just added this as an edge case. Ideally this won't happen in our test run. Okay, so but this case would happen wherein nums is of length 1. So in that case we have only one house, so we just return nums of 0. Okay, and then next case is what? Nums of length 2. In that case we can return the max of these two, so we don't need an array for that, right? So that's why we don't form an array, we can just directly return it. Okay, and then we define our helper function for the dynamic programming. Firstly, we initialize the DP array. So here DP is equals to 0 into length of nums. So basically, this would form a DP array of length n, all filled with zeros. So after this step, what would be the value? So if we have nums of length 4, then DP array would form for what? Length 4, all filled with zeros. Okay. Next is we're filling DP of 0 is equals to nums of 0. This is something we just looked at here, right? This is basically first house case. And next is this is the first two houses case. So this case, right? So basically this is what maximum of these two values. Okay. And next is the typical DP case. So here we fill the DP array starting from the range 2 to length of nums -1. So here this is exclusion range. That's how it would generate the indexes from 2 to length of nums -1. And next here for each index we just choose to rob or not based on the value we get. So we got the founder from here, right? That is just max of DP of I-1 and nums of 5 plus I-2. So this is the case of skipping the current house, and this is the case of robbing the current house. So we just add the value of the current house and the robbery value we get from previous part 1 DP array. Okay, so basically here we consider, right? So if we consider for DP of 2, we have to check max of DP of 1 and 1 plus DP of 0. Okay, and at the end after completing all iterations we return DP of -1. Basically this is the last element which stores the maximum amount of money we can draw from all the houses. Okay, so after the helper function is defined, we can just call this helper function with our array split. So basically here we call the helper function for the two ranges we have. First range is what? 0 to n-2, and next range is what? 1 to n-1. Okay, so here what does this mean? This means that we just checking this range 0 to n-2. Okay, so this is exclusion range, that's why it would pick only till n-2. So this is what the case of a1 to n-1. Okay, so we have to return the maximum of these two possibilities. That's why we using the max function here. So we just look here, right? So here we had 4 coming here and we have 3 here. Max of 4 comma 3 is 4. So that's why we return 4 here and we choose the max function for the same here. So what are complex here? The time complex is O of n, where n is the number of houses, because for each house we compute only once. That's why it's O of n. And the space complex is O of n due to the DP array we have. So this DP array would have the same length of nums. That's why it's O of n space. Okay. So I got the code ready here. Let me try running this. So this is the accept solution with the 3 test cases. Let me try summon this. So this is accept solution for all the test cases. So let's look into approach 4, which is space-optimized dynamic programming approach. So here, what is our intuition? Instead of using an entire array to store the maximum profits, we can use 2 variables to keep track of the last 2 maximum profits, thereby reducing the space complexity. Here, instead of O of n space complexity, we will be having O of 1 space complexity. So how can we achieve it? So basically, if we observe this previous approach, there we were using entire array, right? So but even if we use entire array, for the current iteration, we will be using only 2 variables, which is DP of I-1 and DP of I-2. What if we can use only 2 variables here? If we can use only 2 variables, then that is sufficient to fill the current iteration, right? So the 2 variables here are pre-2 and pre-1. So what is a pre-2 here? This would be the max profit from house I-2, and pre-1 is what? Max profit from house I-1. Okay, so this is the idea here, guys. So now let's look into the algorithm. So insert the 2 variables pre-1 and pre-2 to keep track of the maximum profit from the last 2 houses. In step 2, loop through houses, updating the 2 variables at each step to reflect the current maximum profit. In step 3, return the maximum profit after considering all houses. So let me just explain the algorithm here. So here we have 1, 2, 3, 1 as an array, and then we split into 2. 1, 2, 3 and 2, 3, 1. Basically, we consider these 3 and these 3. Okay. So here this is what the DP value we had for the previous approach. Now we are achieving the same thing using the 2 variables. So let me just do a dry run for that. So firstly, what is the value of pre-1? It is equals to 0, and pre-2 is equals to what? It is also 0. And now current iteration deals with the filling of the DP array, right? So compare like that. Okay, it is not filling the DP array, but I will just show you the parallels between these two. So firstly, there we were filling the index 0. Okay, And now how are we filling this? So we are taking the max of pre1 and nums plus pre2. So max of pre1 is what? 0, and nums is what? Currently it is 1. So here for this 1 2 3, currently the nums is what? 1. So it is max of 0 comma 1, which is 1. So here we got the same result, right? So here dp of 0 is 1. So we also getting for the current iteration it is 1. And next, so for the index 1, what we are doing again? But before we go to index 1, we will be changing our pre1 and pre2. So here pre1 is what? It's a maximum profit from the house I minus 1. So for that we have to update, right? So the house I minus 1 profit would be stored in what? In current variable, right? So that's why we have to change the pre1 to current. So the pre1 would become what now? It is 1. Now pre2 become pre1 because it was the value of profit till I minus 2 houses, right? So that's why pre2 become what? 0 now. So let me just put a formula here. It is just the max of pre1 and this current nums value plus pre2, okay? And for each iteration we update pre1 is equals to current and pre2 is equals to pre1, okay? So here for the current iteration, which is first index, what will be doing? We'll be doing the max of pre1. Pre1 is what now? 1, and num plus current num is what? It is 2, plus pre2 is what? It is currently 0. So here it is 2, max of 1 comma 2 is 2, okay? And before we go to next iteration, we have to update our pre1 and pre2, right? So pre1 would become what now? It is 2, and pre0 is what? The previous value of pre1, which is 1. Okay, so these variables are now updated. So now we are at the index 2. So here it is max of what we have, it is pre1. So pre1 is what? 2, and then next what we have? Num plus pre2. Num is what? 3, plus pre2 is what? 1. So basically max of 2 comma 4 is what? 4. So you got the approach, right? Here also we got the same values for DP array if we fill this using the current approach. So here we are not actually filling the DP table, but I just showed you for each iteration what happens, okay? So you got the idea, right? So hope it is clear for you. So here also we got the same values 1 to 4, 1 to 4, okay? So that's the idea, guys. So let's look into code. So firstly we have the same edge cases as previous approach. So everything is same here. In house robber method we have this difference, wherein we were using the DP array, but here we will be using this two variables. So this pre2 and pre1. So pre2 is what? The max profit from house I minus 2, and pre1 is what? Max profit from house I minus 1. Now we just iterate to the houses. So in step 3 we just getting the max of robbing or not. So for that we have to get the max of pre1 and num plus pre2, okay? So basically here if you take the pre1, that means that we are skipping it. So if you take the num plus pre2, that means that we are robbing the current house, okay? And that value would be stored to current. So for the next iteration we have to update our pre2 and pre1. So pre2 has to hold the max profit till I minus 2, right? So now for the next iteration pre2 will be having the value of pre1. That means that it will be having the value of I minus 2. Okay, and next pre1 would be having the value till I minus 1 houses, right? So for the next iteration, if we store the current value, then it would be the value of I minus 1, right? So that's why we update the pre1 to current, okay? So at the end, we return the pre1 because pre1 is what? It's a current house value, right? So after the completion of this iteration, pre1 would be storing the value of what? The last index in the DPR if we compare. So that's why we return the pre1, okay? So here in step 6, we handle the circular condition. This is the same case, right? So here we just perform the same thing, okay? So let's look into the complexities. Time complexities often because we iterate through list of the houses once. And the space complexities often because we use only two variables to keep track of the maximum amounts. So here the space we use inside the solution is not dependent on the input array. So it's not growing with the input array. That's why it's often because it's always two variables we use, okay? So I got the code ready here. Let me try running this. So this accepts solution for the three test cases. Let me try summon this. This accepts solution for all the test cases and beats 100% of users. Cool, right? And that's your wrap on solving the house Java 2 problem using 4 different approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.